Good morning, good afternoon, good evening, or good whatever, or whenever you are actually listening to this. Today we're going to start a completely new tack where we learn about a second important class of languages other than the regular languages. This class is the context-free languages. They include all the regular languages and more. The most common description for these languages is a context-free grammar. We'll see the definition of these grammars and the way these grammars define languages, which is through derivations. We're also going to introduce a related notation called Backus-Naur form. The two most important applications of context-free grammars are probably in processing natural languages and computer languages. I'm going to focus on computer languages, where almost every language today has its syntax defined by a context-free grammar in the Backus-Naur notation. Grammars are also essential when designing a parser for the language, that part of the compiler that puts together the tokens of the language into the proper structure. For example, the parser discovers the order in which arithmetic operators are applied in an arithmetic expression and groups statements properly so their execution sequence is as intended by the programmer. A context-free grammar defines a language by a mechanism we will soon learn. Every regular language has a context-free grammar describing it, but there are also languages that can be described by a grammar, but that are not regular. On the other hand, the context-free grammar is still a relatively weak formalism. There are some languages that are simple to describe yet have no context-free grammar. Many of the languages in the context-free class that are outside the regular languages are languages that involve nested structures such as the patterns of left and right parentheses that we call balanced. The central elements of a grammar are variables. These are symbols that generate particular sets of strings. One of these symbols, called the start symbol, will generate the entire language, but we can have many others to help us in that definition. The variables, or rather the sets of strings they generate, are defined recursively in terms of one another. The rules that define the languages of the variables are called productions. Each production has a variable on the left, say A, an arrow, and 0 or more symbols on the right. We'll draw, say, X and Y on the right that serve as the definition. A rule like this says that the concatenation of the languages represented by X and Y is a subset of the language represented by A. A variable may have several productions, and its language is thus defined to be the union of the languages described by the right sides of each of its productions. But remember, all of this may be recursive, so grammars are in fact far more powerful than the regular expressions we can build from unions and concatenations. For our first example, let's consider the language that we showed not to be a regular language, the set of strings with a form of n zeros followed by the same number of ones. Here is a grammar for this language. There are two productions or rules and only one variable s. The first production, this one, is a basis rule. It says that the string 0, 1 is in the language of S. The second, this, is an inductive rule. It says that if W is a string in the language of S, then 0W1 is also in the language. That rule lets us build longer and longer strings, at each step adding 1 0 to the beginning and 1 1 to the end, so we always have the same numbers of zeros and ones with the zeros preceding the ones. Now let's make precise our informal introduction to what context-free grammars look like. The terminals of the grammar are analogous to the input symbols of an automaton. They form the alphabet for the language being defined. The variables, or non-terminals, are something like states of an automaton, but they are more powerful. One variable is called the start symbol. It is the language of this variable that the grammar defines. Any other variables are used as auxiliaries, but we can think of them as internal to the grammar, and their languages are not visible outside. The productions of the grammar, which are akin to the transition function of an automaton, have the form of a variable on the left, sometimes called the head, an arrow, and a string of 0 or more symbols which can be terminals or variables. These are sometimes called the body of the production. We have a convention about the letters used for certain symbols and strings. These conventions are more complex than the convention we use to distinguish input symbols, little a, little b, and so on, from strings, w, x, and so on. But they're really important as a reminder of the roles different components play, and it is something worth committing to memory early on. First, we use capital letters at the beginning of the alphabet as variables. However, S is also normally a variable. In fact, it will be the start symbol in many grammars. On the other hand, lowercase letters at the beginning of the alphabet are terminals. This convention agrees with our earlier convention that made these letters stand for input symbols, since there is a good analogy between the input symbols of an automaton and the terminals of a grammar. Capital letters near the end of the alphabet are used for symbols that could be either terminals or variables. We typically don't know which. Lowercase letters at the end of the alphabet stand for strings of terminals only. Again, this matches our earlier convention. And we use Greek letters at the beginning of the Greek alphabet for strings that may consist of both terminals and variables mixed. We'll design a grammar for the language of strings with the form 0 to the n, 1 to the n. The terminal alphabet is 0 and 1, of course. We need only one variable in this case. We'll call it S. S will be the start symbol. There's no other option since it is the only variable. And here are the productions which we explained earlier in our informal discussion. The first production generates only the string 0, 1, and the second production puts a 0 and 1 at the beginning and end, respectively, of a shorter string in the language. A derivation consists of a sequence of strings that typically have both terminals and variables, although they could have only one kind of symbol or even be empty. We start with the string consisting of just the start symbol. At each step, we find a variable to replace, say A. The productions for A, or the A productions, are those that have A on the left side, that is, the head of the production. We replace this A by the right side or body of the production. We can then repeat the process as many times as we like until we are left with only terminals, at which point no replacement is possible, and we have in fact generated a string that is in the language of the grammar. Here's what the replacement looks like. You take any string that has an occurrence of some variable A, and anything to the left and right, terminals and or variables, which is what the alpha and beta we have here suggest. You take an A production whose body is gamma, and you replace the A by gamma. Here is an example derivation. We always start with a string that has just the start symbol S. We choose the second production, so S is replaced by 0S1. Now we replace the S again using the second production, and again we replace the S, but this time we use the first production whose body is just 0 or 1. We are now left with a string that has only terminals, and this string cannot be subjected to further replacements. You should be aware that in more complicated grammars, variables can be replaced by strings that contain 2 or more variables, and when that happens we have lots of choices of what variable to replace at each step, and derivations can be much more complicated. The double arrow symbol represents single steps of a derivation, and just as we extended delta to many steps for automata, we need to have a notation that means any number of steps for a derivation. This is the arrow star symbol, and we define it inductively. Okay. The basis is that in 0 steps the string can't change, so any string goes to star itself. The inductive step lets us get from alpha to beta using any number of steps, including 0 steps. That's that. And then, with one more step, get from beta to gamma. The conclusion is, then, that alpha goes on some number of steps to gamma. Here's an example using the same grammar as before and the same derivation sequence we just discussed. We can conclude that S goes to itself in 0 steps. That is, we just start here, don't go anywhere. So we can conclude that S goes to star itself. Then inductively, S goes to 0, 0S1, rather, 0, 0S1, and 0, 0, 0, 1, 1, 1. Notice also that we don't have to start with the start symbol. It is also true, for example, that 0S1 goes to star 0, 0, 0, 1, 1, 1. Okay. That is, anything along the derivation sequence goes to any later, goes to itself and any later position along the sequence. A sentential form for a grammar is any string derivable from the start symbol. That is S arrow star the sentential form. The sentential form can consist of any mix of terminals and non-terminals. The language of a grammar G is the set of terminal strings W such that the start symbol of G derives W. Here's an example grammar that is just a little different from the previous one. Here the basis rule is that S goes to epsilon rather than S goes to 0, 1. Note that epsilon is a perfectly legitimate body for production, and its effect is to make the variable on the left disappear. As a result, this grammar can derive the empty string along with all the other strings that have some number of zeros followed by the same number of ones. That is, the language of this grammar is the set of 0 to the n, 1 to the n, such that n is at least 0, while the previous grammar had at least 1 as the condition on n. The class of languages called context-free languages consists of all those languages that are defined by some context-free grammar. We now see that there are context-free languages that are not regular languages, such as the 0 to the n, 1 to the n example just given. However, there are languages that are not context-free, and the intuition is that context-free grammars can count 2 things, but not 3. Thus, an example of a language that is not context-free is 0 to the n, 1 to the n, 2 to the n, say such that n is equal to or greater than 1. That is, you cannot match both the zeros against the ones and the ones against the 2 at the same time. I want to introduce a notation called BNF, or Backus-Naur form, which you may have seen in manuals for programming languages, and which is closely related to context-free grammars. BNF has a number of extensions to the grammar notation we use, and these extensions are useful in manuals but don't add any power. BNF-style notations were used for 2 of the original programming languages. John Backus used it in the original description of Fortran, and Peter Naur used it in the original description of Algol. In BNF, you usually use a word to describe a variable, for example, statement, if the intent is that this variable will generate all the strings that are valid statements of the programming language. Conventionally, these words are put in triangular brackets to tell us they are variables rather than terminals. Some terminals for a programming language are single characters, just like in our formal context-free grammars. For example, the plus sign or semicolon are commonly terminals in the grammar for a programming language. However, other terminals are really reserved words like if or while. And we see these shown either in bold or underlined depending on the style used to remind us that they are single symbols. In BNF we often find colon equals used in productions rather than the arrow. We also find a vertical bar used to list several production bodies that have the same head. That is a useful convention that we shall use in formal grammars as well. For example, our original grammar can be written with S once on the left side and the bodies of the two S productions listed with the bar connecting them. Another extension of BNF is similar to the Kleene star, but it means one or more rather than zero or more. We follow a symbol or a bracketed expression by ... to mean one or more occurrences of the symbol or the symbols within the brackets. So here is an example. We have one variable, digit, with the obvious 10 productions, all grouped together with the bars. Then we have one production for the variable unsigned integer with right side digit ... that is one or more digits. In general, we can replace alpha ... by two productions. Let A be a new variable that generates all sequences of one or more alphas. A has two productions with bodies A alpha and just alpha. You should be able to see how A can be replaced by any sequence of n alphas. Just use the first production n-1 times and the second production once. For example, here is a grammar for unsigned integers where the BNF d ... has been replaced by these two productions. These generate any sequence of one or more Ds. Then D generates each of the 10 strings consisting of a single digit. That's, of course, that. We can make part of a production body be optional if we surround it by square brackets. For example, many programming languages have both an if-then and an if-then-else construct for statements. We can see this as an if-then statement with an optional else clause. In BNF, we put brackets around the else clause to make it optional. That's essentially this stuff there. We can replace an optional alpha by a new variable A. This variable has two productions, one with a body alpha and the other with the empty string for a body. Thus, the alpha can be either there or not when we expand the new variable A. Here we're using I for if, T for then, and E for else, and the semicolon is another terminal standing for itself. S is the start symbol standing for statement, and C is another variable representing conditions. We really need to add productions for conditions, but I haven't done so in this fragment of a real grammar. Notice that A is a variable standing for an optional else clause. It can be replaced by a semicolon, an else, and another statement if we want to have the else clause there, or by epsilon if we just want an if-then statement with no else clause. Curly braces are used in BNF for grouping several different elements. You need this, for example, if you want to have a repeating group of elements in a ... or one or more construct. For example, it is common in programming languages to allow a statement list to be one or more statements. The statements are separated by semicolons, so there is one fewer semicolon than statements. That is, a statement list consists of one statement, that's this, followed optionally by one or more groups consisting of a semicolon and a statement. There. Brackets form a group, and then finally the ... applying to the group says one or more of these groups. Finally, you have the braces, and those braces say that the whole thing is optional. To translate groups to our original notation, just create a new variable A for the group. A has one production whose body is the group. Here's an example of a production that uses all three BNF features, one or more, optional, and grouping. It says a list of statements L is a single statement S, optionally followed by one or more groups, each group consisting of a semicolon and a statement. The first thing we'll do is replace the group semicolon S by a new variable A. A has one production in which it is replaced by the thing it stands for. That's this guy right here. And next, we'll introduce a new variable B, which stands for the optional A dot dot dot. B has two productions. It is replaced either by the A dot dot dot, that would be this choice, or it is replaced by the empty string. Finally, we replace the A dot 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 in the B productions by the new variable C. The productions for C, which are here, allow C to be replaced by any sequence of one or more A's. When a sentential form has a number of variables, we can replace any one of them at any step. But what string of terminals a variable ultimately gets replaced by is independent of what else is in the sentential form. That's actually where the term context-free comes from. As a result, we have many different derivations of the same string of terminals. We can restore some order to the world by requiring that a particular variable be replaced at each step, although we cannot demand that any particular production be used for the replacement. One reasonable rule is to require that the leftmost variable be the one replaced at each step. This rule restricts us to what are called leftmost derivations. Similarly, we could require that the rightmost variable be replaced at each step, and that gives us the rightmost derivations. The double arrow with an LM subscript, that's this, represents one step of a leftmost derivation. That is, on the left of the arrow LM, we must have a string of the form WA alpha. Here you see one. That is, since W by our convention has terminals only, A must be the leftmost variable in the string. On the right is the same string with the body, say beta, that, of some A production replacing A. The symbol consisting of the double arrow with a subscript LM and a star, that's this, means becomes by a sequence of 0 or more leftmost derivation steps. Let's introduce another very simple grammar that generates a language that is not a regular language. This grammar has only one variable, but unlike the 0 to the n, 1 to the n grammar, there are productions with more than one variable in the body. This grammar generates strings of balanced parentheses, those strings that are legal in arithmetic expressions. The last production, here's its body, says that a pair of matching parentheses is balanced. Of course, the left parenthesis must come first. The middle production, this, says that if we put matching parentheses around a balanced string, it is still balanced. And the first production, this, says that the concatenation of two balanced strings is balanced. We need to prove that every string of balanced parentheses can be generated by this grammar. The proof is not too hard, but we're not going to do it here. Here's an example of a leftmost derivation. We start with just S, so that is the leftmost variable. Okay. We replace it by two S's at the first step. There we go. Next, the first of these S's must be replaced in a leftmost derivation. We choose the second production for the replacement. There we are. At the third step, the first of the S's must be replaced, and here we choose the last production in the replacement. That's giving us that. Okay. At the last step, we have only one S, and that naturally is the one we replace. We have chosen to replace it using the last of the three productions, so now we have a terminal string and are done. The arrow star leftmost notation can be used to express 0 or more leftmost derivation steps. So for example, S is related to the terminal string by this relationship. It is also related to itself and all the other steps in the derivation by the same relationship. And in fact, each step is related to itself and all the following steps. Okay. Here is an example of a derivation that is not leftmost. The problem is that at the second step, the second s, rather than the first, was replaced. Rightmost derivations are defined quite analogously to leftmost derivations. The arrow with an rm subscript, this, means that the rightmost variable was replaced at the step. Notice that the string on the left, which is this, has w, which must be a string of only terminals following the variable a that gets replaced. Thus a is surely the rightmost variable. And the arrow with an rm and a star means 0 or more steps of a rightmost derivation. Okay. Here's our balanced parenthesis grammar again. Now we have a rightmost derivation of the same string as before. Notice that at the second step, the second s got replaced rather than the first. S is related to the terminal string by the arrow star rightmost operator, and as for leftmost derivations, each step in the rightmost derivation is related by this operator to itself and all the steps that follow. Here's an example of a derivation that is neither leftmost nor rightmost. See how at the third step, the middle s is replaced. Also, notice that the second step is correct, but ambiguous in a concerning way. One of the s's here, one of these two, got replaced by two s's, but we don't know which.